the benzene ring undergoes this very special type of reactions, which is called electrophilic aromatic substitution reactions, that when a benzene ring reacts with an electrophile, it undergoes substitution. Let's draw a general scheme for the reaction, and then we see how we can apply it to specific examples. So if we take the benzene ring in general like that, and then if we react it with an electrophile, the electrophile then gets bonded to one of the carbons on the benzene ring. Of course, this reaction is substitution because that hydrogen has been substituted by the electrophile. That's why it's called substitution. Of course, it's electrophilic because the reaction is between the benzene ring and the electrophile. Of course, the benzene ring behaves as a nucleophile. It is aromatic because benzene ring, of course, is aromatic. As we will see also later on, why is benzene aromatic? Now, let's take specific example of an electrophilic aromatic substitution reaction, and that's if the benzene ring or if benzene reacts with bromine in the presence of FeBr3, the product is bromobenzene. This is a very interesting electrophilic aromatic substitution reaction. Benzene ring or benzene reacts with bromine in the presence of FeBr3. If benzene ring is attempted to react with bromine without iron 3 bromide, then there will be no reaction. Remember, benzene is not an alkene. Benzene does not undergo the reactions of alkenes, which are electrophilic addition reactions. For example, if you take a test tube containing cyclohexene and then you add few drops of bromine, there will be an instantaneous reaction. The orange color of bromine disappears immediately, which is indicative of the fast reaction of alkenes with electrophiles. But if we try to do the same on benzene, there will be no reaction. Benzene does not react with halogens in electrophilic addition reactions. Now, if a catalyst is added, such as a Lewis acid catalyst, in this case it's iron 3 bromide is added with bromine, then the reaction takes place, but the reaction is not electrophilic addition. Anyway, it is substitution. Now, it is substitution because benzene is aromatic. That benzene is also aromatic, so whatever intermediate is involved will regain aromaticity. It's thermodynamics here. Okay, so let's now try to draw or to postulate, if you like, a mechanism for this reaction. Where is the electrophile? Well, clearly, if this E is that Br, then the electrophile here must be Br plus. So it's really, that's what we are looking for. We are looking for Br plus to form. So this is the electrophile, if you like, that is involved or has to be involved actually in this reaction. So whatever reagents are mixed here, they must react with each other initially to give that electrophile which is required to react with benzene for this electrophilic aromatic substitution reaction to take place. So how does that happen? How does that ion or how does that electrophile form if bromine and iron 3 bromide react with each other? Remember, this is bromine and this is FeBr3. Remember, FeBr3 is a Lewis acid. It's a Lewis acid catalyst, of course. Now, if it's a Lewis acid by definition, then it should accept a lone pair. And of course, this is the Lewis acidic center. It's iron, actually, of course, not bromine. That's the Lewis acidic. It is the iron center that accepts a lone pair, and thus it's a Lewis acid. So where would that lone pair come from? Well, it should come from bromine. Each of these bromine atoms in bromine molecule has 3 lone pairs. So there are 3 lone pairs actually on each of these bromine atoms in the bromine molecules. We can show electron movement like this. So we take a lone pair from one of the bromine atoms to the lowest acidic center, which is iron, to give this intermediate. This intermediate, but now bromine has two lone pair, and therefore it carries, of course, a formal charge of +1. Remember, it's 1, 2, 3, 4, 5, 6. Of course, non-bonding plus half bonding, so 4 plus 2, that's 6. 6 from the normal number of valence electrons of bromine, which is 7, and that's, of course, +1. So the formal charge of bromine here is +1. Now, this intermediate would undergo this bond cleavage, so this Br-Br bond will now be broken, releasing electrons on the positively charged bromine to give Br plus. As a result, this gives Br plus, of course, Fe. This time it's FeBr4 minus, where iron has now 4 bromines bonded to it. So iron is actually negatively charged. So this is the electrophile that we are looking for. So what will happen now is that benzene ring will now approach this electrophile. So we can show this using Cayley arrows like that. Benzene reacts with this electrophile. So the one of the carbon-carbon double bonds is broken, and this intermediate is, as a result, formed. Remember, there are hydrogens here. So there is hydrogen here. There is hydrogen here. Now, as a result of this carbon has lost its electron share, because when this carbon-carbon double bond is broken, it's actually the pi bond that's broken, the pi bond connecting or bonding these two carbon atoms together. The two electrons that are released as a result are now used to make a bond between that carbon and that bromine. So this carbon is satisfied with respect to the octet rule, but this carbon has lost its electron share, so therefore it must carry a positive charge. This is a carbocation intermediate. But if you look at this carbocation intermediate, it's actually non-aromatic or anti-aromatic. It's not aromatic here. It has lost aromaticity, therefore, benzene ring, as a result of this initial step. Therefore, this step will not be very fast. It's actually a slow step, a slow reaction here so far. But once this carbocation intermediate is formed, it can regain aromaticity if it loses that hydrogen. This hydrogen here, of course, that's bonded to that carbon. And of course, that hydrogen can be lost in the form of a proton to a Lewis base or to a base in general. And that Lewis base is actually this FeBr4 minus. So the FeBr4 minus can come, take off that proton, and the hydrogen-carbon bond is broken, and a new carbon-carbon double bond is formed to give the final product. And if you look at this product, it's actually aromatic. So this is aromatic, and of course benzene itself is aromatic. But this carbocation is non-aromatic or not aromatic carbocation. This non-aromatic carbocation regains aromaticity, and since this is supported by thermodynamics, this second step is actually fast. So this is a fast step. This step where benzene, the initial step, the reaction between benzene and the electrophile is actually slow. So this step is slow. Since it's slow, it's the rate determining step. This carbocation, remember, is involved in electrophilic aromatic substitution, but once the carbocation is formed, and given the fact that it is not aromatic, it can regain aromaticity if it loses this hydrogen to a base. So a base, a Lewis base, an organic base, a Lewis base in this case, takes off that proton, the carbocation regains aromaticity. The reaction overall is an electrophilic aromatic substitution. The product is bromobenzene. The reagents are bromine and iron 3 bromide. The electrophile involves here Br+. So this is a bromination reaction, an example of a bromination reaction of benzene as an example of an electrophilic aromatic substitution reaction.